Today I'm going to be presenting some work from the first year of my PhD, which I'm working on with Fabian and also Sarah Wilks at the University of Otago. And my talk is called Graded Arrays of Vertical Barriers, Rainbow Reflection and Broadband Energy Absorption of Water Waves. So rainbow reflection is this phenomenon that can occur when you've got...
we can't see the slides, unfortunately.
Oh, sorry. Let me just... Is that better?
Yeah, good.
Cool. So rainbow reflection is something that occurs when you've got this graded or spatially varying array of resonators. And so when you send some sort of broadband wave signal into this array, the different frequency components of the spectrum can spatially separate into their frequency components. So that's probably something that's better seen with a couple of examples. So this is one of the first places where this phenomenon was discussed, and that's in the field of optics. And so what you're seeing here is on the left, you've got an ordinary waveguide, and on the right, you've got a tapered metamaterial waveguide with some graded chemical properties. And so what happens is when you send in a broadband wave signal, it separates out into its frequency components, and in particular, low frequency waves are going to propagate further than high frequency waves. So this is another motivating example from acoustics, and here you're seeing a two-dimensional array of Helmholtz resonators, which are getting bigger in size from left to right. And as a consequence of that, the low frequency waves are going to propagate and amplify further towards the right than their high frequency waves. So this third example is one of the only examples so far in the field of water waves, which is actually by Luke Bennett's et al. And so what you're looking at here is a top-down view of an array of C-shaped cylindrical resonators, which are increasing in radius from left to right. And a consequence of this is that the low frequency waves are going to propagate and amplify further towards the right than the high frequency waves. So I wanted to study this first of all, in just the simplest geometry you can imagine for this kind of thing. So in water waves, what came to mind is this graded array of vertical barriers. So here, what you're seeing is you've just got a free surface at the top, you've got a seabed at the bottom, and these lines here are your vertical barriers, which we assume are infinitely thin. And the reason that this works for the problem, what we predicted that it would work, is that these cavities between the two barriers can act as a resonator, and this is quite well understood in the literature. So to model this problem, I'm going to use linear water wave theory. And so basically you assume that the fluid is inviscid, irrotational, and incompressible, and that it's undergoing time harmonic motion. So you can just express the velocity of the fluid as the gradient of some scalar potential, which satisfies Laplace's equation, as I'm sure a lot of you are already aware. We assume that the free surface is linear and that we've got no normal flow on any of the fixed bodies. So this includes the seabed, and it also includes the fixed barriers. So the forcing to this problem is supplied by a plane wave, which is traveling from left to right. And we've also got a Sommerfeld radiation condition at the far field. So I won't go too much into the solution of the problem. But basically, the single barrier problem is solved using separation of variables. And then the problem becomes solving for the unknown coefficients. So you just reformulate that as an integral equation, which can be solved numerically using a Galerkin method. And then for the multivariate problem, you just use a scattering matrix method, which I don't really want to go into in any more detail than that. So once you've got a pair of barriers, we can start looking at the resonance that occurs between them. And the intuition for this resonance is that the fluid, when the barriers are really close, the fluid between the two barriers is essentially moving just up and down. And it's that's actually an oscillation about its hydrostatic equilibrium. So if you make that assumption for the parameters I've chosen here, you would expect the resonance to occur at this dashed line. But when you actually model this using a finite separation of the barriers, you get these peaks which are occurring at slightly lower frequencies to the hydrostatic prediction. But that doesn't seem to matter too much. You're still getting a pistoning mode where the fluid between the two barriers is just moving up and down. So this is just a time domain plot for one frequency component, and the colors are just showing the velocity potential. So now that we understand the resonance which occurs between a pair of identical barriers, we can now go on and start looking at graded arrays of barriers. So just for this case example, I'm creating a system where you've got 9 cavities, and I've chosen the parameters of the barriers so that the resonance of the first cavity should approximately occur at 1.6 per second, and this is angular frequency. And then the resonance of the second cavity should occur at 1.5 per second, and so on, all the way down to 0.8 per second. So the cavities should be getting bigger and bigger to account for this. And so what I'm going to show you now is just a frequency sweep that's going through a frequency interval and just showing where the energy is amplifying. So for low frequency waves are propagating and they're amplifying in the rightward cavities, and the high frequency waves are amplifying at the cavities further towards the left. So let's just play that again. Cool. So now that we know that the frequency components are separating out and the energy is being localized in these kind of predetermined locations, it's kind of natural to ask, can we design an energy absorbing apparatus which is going to take advantage of this? And so the system I looked at next is kind of given in this schematic. So you've got all these vertical barriers like we had before, but now I've added a piston which is positioned above each cavity, and the piston is restricted to move up and down and heave, and the piston is also coupled to well, it's shown as a dashpot here, but you can just think of it as friction or any kind of basic power takeoff model. There's nothing nothing fancy here, it's all linear. So to extend the problem to the case where you now have pistons, the main thing you have to do is just model the interaction. So the easiest way to do that is you assume that the pistons are oscillating around their equilibrium submergence, which is just given by Archimedes' principle. Then from that, you can just write down the equation of motion and the frequency domain where we've linearized around that submergence. And this term here that just gives the damping or the power takeoff. You've also got a kinematic condition, which is just telling you that along the wetted surface of the piston, the velocity of the piston and the velocity of the fluid are the same. So that's pretty standard. And so after solving this problem, which is a little bit more complicated than the previous one, but not too much worse, you can measure the absorption, which is associated with a particular device. And so the standard way, as I'm sure most of you have seen, is to subtract transmission and reflection from 1, and that kind of gives you the proportion of energy that's been removed. But you can also do some calculation, and you can just view this as the decomposition of absorption by each of the pistons in your array. So that will become important in a few slides. So the next part of this research project was basically just solving a whole lot of optimization problems. And the way the problems work is that at each step, you add 1 cavity to your array, but you also add 1 frequency to your objective function. So we're trying to maximize absorption over a discrete set of frequencies here. So I'll just go through this slowly. And what you're seeing is that the device is getting larger, but the absorption spectrum is getting more peaked, which is representing the increasing number of frequencies that are getting fed into the objective function. And I'll just go through these here. And so one thing you can say about this absorption spectrum is we might not necessarily want it to have this peaked behavior. It would be better for applications if we could get an almost flat curve along here, because we don't want to assume a priori what the incident frequency is going to be. So what you can do at this point, and this was also has been looked at in the acoustics case, but not in the water waves case, is optimizing this over a, so changing the objective function so it's now an integral over this interval here. And that should penalize values like this, where the absorption is quite low. So you get this curve like this, and I've put the colors underneath the curve, which is meant to demonstrate which piston is doing the absorption at that particular frequency. So while we do get this flat curve like we wanted, one thing to be aware of is that the first few pistons haven't really contributed much to absorption over the target interval. They're kind of creating these separate peaks at higher frequencies. And I wasn't really sure what they were doing for a long time. But what my hypothesis is that they have an important role in coupling the incident energy to the deeper cavities where the absorption is actually taking place. Because when you remove these first 2 or 3 cavities, absorption over this interval becomes much worse than can be explained by the contribution to absorption alone. So I'm just going to wrap up here. A couple of future projects which I'm hoping to get started on or have already started on. I'd like to extend the results to an array of cylindrical resonant absorbers in 3-dimension. So that could allow consideration of things like oblique incidence and what the effect of that could be. I'd also like to look at simulating broadband wave packets in the time domain and seeing how the frequency components are actually separating. And a third project is to validate the results of this work, in particular the local energy amplifications in the first half of the talk using Fluent, which is computational fluid dynamics software. And so a preprint of the work in this talk is available on the archive. So thank you, and yeah.
Thanks, Ben. And nice talk. And any questions from the audience? Oh yeah, we got one from.
Yeah.
Can you hear me, Ben?
Yeah.
Cool. That's really nice.